Will the ISS melt? Insane numbers equals insane math equals insane numbers. Welcome to another session of Flat Earth Math. You can relax, there's no trigonometry in this one. The big question that's been going around that is if the ISS is in the thermosphere, isn't it going to get rather hot? And so I decided, everybody has this instinctive feeling that, the thermosphere is hot, but they say the air is very thin. So it doesn't matter because there's not enough molecules to make it hot. So I decided to look at some of the actual numbers involved, and it turns out that the air is very thin, but I wanted to get a figure, and the closest I could get was about 200 pascals, which is about 0.002 atmospheres. So it is thin, but there is definitely some air pressure/density out there. Next, I wanted to consider the velocity of the ISS, because the velocity is it's moving at a pretty good clip. It's a pretty insane number. So let's look at the velocity of the ISS. First of all, the orbital velocity of the ISS is running out at a good clip of 7,710 meters per second. Now, to give you an idea of the magnitude and just how insane that velocity is, the latest developmental railguns, which use magnetic fields to drive the round forward or the warhead forward, are sending out rounds out of the barrel. And this is the muzzle velocity of 3,000 meters per second. So the ISS is orbiting at over 70 or over twice as much as that. And that orbital velocity number, interestingly enough, seems to coincide with a thought experiment that Newton had called Newton's cannon, where he tried to figure out if you had a cannon on a very high mountain and you shot the cannonball out of the cannon at a certain velocity, it would eventually get so far out that as it fell down towards Earth, it would actually start moving into an orbit. And it turned out that this Newton's cannon velocity is very close to that of the ISS's supposed orbital velocity. Pretty crazy, huh? Well, this velocity, this hugely insane velocity, becomes very important in computing drag force. And we know that they have drag force because they say they have to compensate for it occasionally. But just how much drag force are you dealing with here? The reason the insane velocity is important to consider is because it is a huge factor in drag force. Any velocity you have is squared when computing drag force. Now we're just going to compute like a square meter section of the ISS for this to consider the area. And then we're also going to use a drag coefficient. This is based on what kind of geometry of body the drag is acting on. And we'll use the coefficient for a round surface because most of the ISS surfaces appear rounded. So we'll use 0.47 drag coefficient. All these numbers and formulas I got from the FAA handbook on the FAA website. So the government's providing all this. And then P is going to be air pressure. But the problem is, because I'm not very sure about that 200 millibars of pressure, I'm just going to leave it as P for now. Okay? So when we plug all of these numbers into our drag coefficient or our drag formula, it turns out to be 13.9 times 10 to the 6th pascals. So this gives us the number for our leading edge pressure on the ISS. All those leading edges are going to have this pressure of 13.9 times 10 to the 6th pascals. But what does that mean for temperature? Gay-Lussac's gas law states that the change in pressure with respect to the change in temperature is directly proportional. So therefore, the pressure at no velocity, or P0, over the temperature at no velocity, or T0, And this would be measured in kelvins. So the surface temperature reportedly in the thermosphere on external surfaces is affected at about 0 degrees Celsius, or 273 kelvins, since we're measuring in kelvins, or from absolute zero. And so that would be related to the pressure at orbital velocity over the temperature at orbital velocity. So if we plug in the figures as we have computed them, the velocity we've already, or the pressure at orbital velocity, which we've already computed. As you recall, the last time I had left the pressure at no velocity is just P. So you notice here in the formula, you'll notice that in the formula, the P cancels out. Now, we did need a pressure of some kind, or air density of some kind. Otherwise, the Gay-Lussac's formula would go to zero and it wouldn't work. But we know that the thermosphere is not a perfect vacuum, which is actually one of the conditions that Newton set for his so-called Newton's cannon thought experiment. So the fact that we don't have a perfect vacuum, there is going to be atmospheric interference and drag. Now, once we plug all of the numbers into the formula and solve the equation for temperature due to drag, we get the insane temperature of 3,794,700,000 degrees Celsius. So will the ISS melt? After running the numbers, I'll have to conclude that no, it will not melt. It will disintegrate long before it reaches its orbital velocity, and thus proving that insane numbers equals insane math equals more insane numbers.